This is lesson 25, logarithmic functions. What is a logarithmic function? What is a logarithm? You may not have known. You may never even have heard that. And possibly when we're through in the next 30 minutes, you may never want to hear it again. But you will, because logarithmic functions turn out to be quite useful in building models of the real world using algebraic functions. Before we decide exactly what a logarithm is, and we will decide that, I want to go back and look at something we called inverse operations. Every time we've created an operation, we've created its inverse. Let's look at the first visual. We see it says inverse operations, and the arrows sort of relate an operation to its inverse operation. 8 plus 3 equals 11. Once we know how to add, then we know about subtraction. 11 minus 3 equals 8. 5 times 6 equals 30. 30 divided by 6 is 5. Once we know multiplication, we also know its inverse operation, division. 4 to the third, 4 cubed equals 64. We also know that the cube root of 64 is 4, the inverse operation of the third power. Now we have something called 2 to the fifth equals 32. We're not looking for the fifth root of 32. We're looking for a function or operation that when we put in 32 and 2, we'll get out 5. And you see that light blue rectangle. And that light blue rectangle can be replaced by the words, the power of 2 that we raise. I'm sorry, let me rephrase that in a way I like to do it. It's the power we raise 2 to get 32. And that power is 5. Once again, we're given the number 32, we're given the base 2. It's the power we raise the base to get the number. That is, the power we raise 2 to get 32. Now, saying the power we raise 2 to get 32 is a little bit wearing. So someone came up with a name and they called it the logarithm. Let's go to the easel and talk about that. All right, we have, again, this 2 to the fifth equals 32. The base is 2. The power is 5. The number is 32. Another way of writing that in its inverse form is to say that the power we raise the base to get 32 is 5. That is, the logarithm, we abbreviate logarithm, log, L-O-G, base 2 of 32 equals 5. These two statements are identical. Okay? These two statements are identical. And in fact, we'll see in solving logarithmic equations, which we'll do later on in this lesson, what we do is say, okay, if you have something in logarithmic form, we can change it to exponential form. We're all familiar with exponents. We're probably not very familiar with logarithms, so it's a lot easier to deal with. So for example, if I said to you, what is the log base 3 of 81? Okay, and let's just call that x. Well, you might not know, because you never heard the word logarithm before you turned on this tape. We write that in its inverse form, in its exponential form. Here's the base, 3. The logarithm is the power. 3 to the x equals 81. We know what that is. In the previous lesson, we had a problem that involved that. We know that 3 to the x is 81, x must be 4. So we could say the log base 3 of 81 is 4. Okay? And basically what we're going to do every time we use logarithms is talk about the exponential form. It's just a lot easier to do. Ultimately, if you become familiar with logarithms, then you can go ahead and think in terms of logarithms. But generally, it's best initially to think in terms of exponents. Okay? Let's look at the next visual, which simply tells us in with using variables what the log is all about. The log base b of x is y, equals y. Or, writing in exponential form, b to the y equals x. So again, y is your logarithm there. The question now is, can we ever raise a number to a positive number to a power and get a negative answer? And the answer is no, which means we can never take the log of a negative number, at least the log base where the base is positive. And we'll only deal with positive bases. Negative bases get kind of messy. You start taking square roots of negatives, you get imaginaries. We can't deal with that. So our bases are always positive. So since we can't take a positive base and raise it to a power and get a negative, we cannot take the log of a negative number. This will be very important in a short while. Also, since we can't raise a positive number to a power and get 0, we can't take the log of 0. Are there possibly negative logs? Well, let's see. The logarithm is really a power. Are there negative powers? Of course there are. 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. In fact, let's go back to the easel here and talk about a problem like that. In other words, let's turn the page. No reason to get confused here. Let's see, 2 to the negative 3 power is 1/8, then we would say that the log base 2 of 1/8 is negative 3. And we can see that as we got more and more negative numbers, negative 4 and negative 5, this answer would get smaller. So as we took the log base 2 of smaller numbers, our logarithm would become more negative. Something we'll see when we graph logarithmic functions. Okay, let's take a look at some logarithmic equations. And remember, we're going to graph logarithmic functions eventually, but before we do that, we need to look at some logarithmic equations to be able to solve them. And we're going to generally solve these equations by getting them in exponential form. So let's look at the next visual, which is log base 2 of x equals negative 3. That should look familiar. We just looked at something like that. And in fact, as you can see on the second line, which is highlighted, we've taken the logarithmic equation and made it into an exponential equation. The base 2 to the power negative 3 equals the number x. And of course, 2 to the negative 3 is 1/8, and therefore x is 1/8. So there's an example of a logarithmic equation where the number is the unknown. Okay, the logarithm is known, negative 3 in this case, the base is known, and we've got to solve for the number. But again, we solved by changing the logarithmic equation to an exponential equation. Let's take a look at the next visual. The next visual, notice now the x is over there. It's the logarithm. We have the base, we have the number. We've got to solve for the logarithm. The log base 5 of 125 is x. We rewrite that logarithmic equation in exponential form. The base 5 to the power x equals the number, 125. And we know that 5 to the third is 125. We should know that. And therefore, the answer to x is 3. Of course, you can check any of these, but it's quite simple. In this particular case, the log base 5 of 125 is 3. How would you check that? I would certainly use a calculator. You say your calculator doesn't have a base 5 log button. I'm going to show you fairly shortly how to use any calculator that has a log button and be able to find the log for any base. Now, one thing you should notice if you have your calculator, that the button says log. It doesn't say log base 2 or log base 5 or log base 7. It just says LOG log. That means log base 10. It's sometimes called the common, C-O-M-M-O-N, common logarithm. And the reason that LOG is log base 10 is going back before there were calculators, back in the ancient days when I was in high school and Eisenhower was president, we had a situation where to deal with big numbers or small numbers and get square roots and cube roots. We used logarithms. We actually used logarithms with tables, all kinds. It was a big mess. Unfortunately, the calculator has done away with that. You say, if we've done away with that, why do we need to study logarithms? Because the logarithmic functions are important in using models. And log base 10 was used because our number system is base 10. And just as we don't have a little 2 in the square root, because most of the roots we take are square roots, since we use the log base 10 so much, it was written log, log. And the log button on your calculator is log base 10. So let's look at the next visual, which has an equation that involves log base 10. Notice it says the log of x equals 1/2. Now here, we know the base, it's 10. It's not there, but we know it because it's log, means log base 10. We know the power, we don't know the number. We rewrite it in exponential form. 10 to the 1/2, the base to the power equals x, the number. And of course, 10 to the 1/2, the 1/2 power means the square root, and therefore our answer is the square root of 10. If you wanted to get a numerical answer, you take your calculator out, has a square root button, you can find out that the square root of 10 is 3 point something, but the square root of 10 is a fine answer. Okay, let's take a look at the next visual. The next visual has the variable x in the base. The log base x of 8 equals 3/2. The solution is the same. No matter where we find the variable in a logarithmic equation, we change the logarithmic equation to an exponential equation. The base x to the power 3/2 equals the number 8. How are we going to solve x to the 3/2 equal 8? Well, remember, the 3/2 power means we're going to cube and then take the square root. So let's get rid of that 2 in the denominator, that square root. Let's square both sides. And on the third line, which is highlighted, we've done that. We've squared x to the 3/2. From x to the 3/2 to the 2, we multiply the powers, and we get x to the third. And of course, 8 squared is 64. And then to solve x to the third equals 64, we know how to do that. We've done that. We take a cube root of both sides, and we get the cube root of 64, which is 4. We go back to our calculator once we know how to take the log base 4. We'd see that the log base 4 of 8 is indeed 1.5, which of course is 3/2. Now, before we go on and do more work with logarithms, I want to develop certain rules for logarithms. These rules are generally stated in textbooks as here they are, know these rules. Again, my belief is you should know why the rule works. And these rules are greatly related to those rules we talked about in the previous lesson when we dealt with exponents. So let's look at the next visual. And the next visual says we're going to have two numbers, x and y. We're going to take the log base b of those two numbers. And again,